So this video is going to talk you through the integrated spectroscopy problems, specifically question number 1 and question number 2. So with these integrated spectroscopy, you're going to be given the following. You're going to be given the percentage of each one of the elements. You're going to be given an IR. In this case, you're just going to be given the peaks and where exactly the peaks are that are important. And then you're going to be given an NMR, which is this one here. And then on the following page is going to be your mass spec. And really the only thing you need to pay attention to with the mass spec is going to be the molecular ion peak, which is going to be in this case, 74. Now, this is a page that you can use to do calculations on, or you could do it directly on a piece of paper, okay? So I'm going to start with the percentages. So the percentages, again, I could go back to first way we did it, which is converted to grams, divided by its molar mass, and then figure out the empirical formula. Or because I was given the 74, I could do it this way. So that's what I'm going to show you. So I know the carbon is 64.82. So I'm going to take my 0.6482. So I'm going to convert my percentage to decimal, multiply it by the overall mass, which is 74. And then I'm going to divide it by 12 because it is carbon. So when I multiply that all out, I get about 3.99 for my carbon. My hydrogen, my percentage was 0.1360. times 74, again, the total mass, and the mass of hydrogen is 1. So that's why I'm using 1. So this comes out to be 10.06, I believe. And then oxygen, the percentage of oxygen that was given was 0.2159 times 74. The molar mass of oxygen is 16. So when you get this, it's about 0.999. So essentially this is 4. This is 10, and this is 1. So my formula is C4H10O. So I have one oxygen. So what you want to think about is, okay, what functional groups have one oxygen? Then you want to think about, all right, what does my IR tell me? Okay, so I'm going to write C4H10O here on this page, so I have it in front of me. So I have a strong peak at 2900, which again, that tells me I have single bonds. And then I have a broad, strong peak at 3300, okay? That is always going to tell me I have an alcohol, okay, an OH. So that's what that is telling me. So I have an OH. So here's where the hard work begins. I now have my NMR, okay? So to help you out, you have a singlet here. This is a sextet, so there's 6. This is a quintet. This is a doublet, and that is a triplet. So also with this, I'm giving you essentially what we call the integration, or the area underneath the peak. So that means this is equating to 1 hydrogen, this is 1 hydrogen, this is 2 hydrogens, this is 3 hydrogen, this is 3 hydrogen. So again, the issue with NMR is always going to be, all right, where is that functional group going to be? So you could start with, all right, put the functional group on the end of the molecule. So let's put the OH on the end of the molecule and see if that works, okay? So again, start with pencils, okay? Pencils are great because then you could erase them and start all over. So the H that's on the OH is probably going to be this singlet way down field, okay? So I'm not really concerned about that, but I'm really concerned about, all right, what would produce a sextet or a quintet? In this model, would that actually work? So this hydrogen here that's attached to this carbon is going to be what we call way down field, okay? So if you look at your NMR thing, a hydrogen attached to a carbon that has an OH is going to be between 3.4 and 4. So this hydrogen is on that carbon. So it's got to be this peak here. And it's telling me I have a sextet. It's also telling me only 1 hydrogen sees that. And I have 2 here. So something's wrong. Something isn't working out right. And if I look at these two hydrogens, the only neighbor it has is this carbon. Well, how many hydrogens are on that carbon? Only 2. So N+1 rule would mean that these hydrogens would have to be a triplet. And this is definitely not a triplet. So that is telling you that that OH can't be on the end, okay? So then what you want to do is just kind of move your OH and see what if I put it on this carbon, okay? And realize because this is a small carbon molecule, if I put it here as well, it would be the same idea. So let's see if this works. Let's see if this works. Now, again, we are focusing on the hydrogen that's on the carbon that has the OH, because I know this has to be that hydrogen. So if I draw it this way, this hydrogen, I'm going to be this hydrogen, okay? I want to look at my neighbors. Well, I now have 2 different neighbors. I have neighbor here, which has 3 hydrogens on it. And then my other next door neighbor has 2. So 2 plus 3 is 5, plus 1 is a sextet. So this looks pretty good. Okay, that looks pretty good for what that is. So let's think that this hydrogen here, again, you might want to use highlighters for this, is going to be that singlet. And let's think that this hydrogen is now going to be that sextet. Okay, so let's see if this is now going to work. Okay, chances are the triplet about 1 is probably going to be a CH3 like I see here. So I am jumping ahead here. But these hydrogens are going to be this particular triplet, that particular triplet. Okay. All right, so now I want to look at these hydrogens here, okay? These hydrogens here only have 1 neighbor, okay? Please remember, the oxygen is going to block the orange hydrogen here. The hydrogen's directly attached to it, so you can't see that hydrogen. The only hydrogen you could see is this one. So again, if these are the hydrogens that I'm looking at, so I'm going to color those in yellow, okay? They only see 1 neighbor, so they have to be a doublet. They have to be a doublet. Well, we have 1 doublet here, and it's pretty close to this triplet, which is, again, is CH3 on the end of the molecule is going to appear somewhere around 1. The reason you don't see it is 1, it's a doublet, and 2, it's right next to that OH. So it's going to be influenced a little bit by that oxygen. So that's why it's further to the left. And so that one makes pretty good sense. So the only one we don't have an answer to is the quintet. Okay, so now I have 1 more color, so make this purple. Okay, so this one, again, is only 2 hydrogens. Okay, the purple ones are only 2, and let's see the neighbors. Okay, so I have a neighbor here. Those are 3 hydrogens, so 3 people living in that house. And then on this carbon, there's an additional 1, so 3 plus 1 is 4, plus 1 is your quintet. If you don't have colors, you could also do arrows. Okay, so you will see that in my answer key. You could just point arrows to things and say this hydrogen is here and this hydrogen is here. Okay, but that is the structure of this particular molecule. This is the structure for this particular molecule. And we could then name it, it's off the 2nd carbon. So this is called 2-butanol. Again, that's how you name your alcohol. Okay, so let's try the next one. So see if you could pause the video and see if you could try this one on your own, and then I will come back with the answer. Okay, so for problem number 2, again, I'm using the same method as I did with 1. I'm taking the percentage, multiplying it by the overall molar mass peak, and dividing it by their respective molar masses. So when I do that, I get C7H14O. Okay, so 1 oxygen. Again, sorry, there's so many pieces of paper. Okay, but this is your molar mass peak of 114, 114. Okay, so now I go back to my IR. And I see that I have a strong stretch, at 2900. So that's all single bonds. And again, we're not going to see multiple functional groups. strong stretch at 17, 20. That's going to be a ketone, possibly. Okay. And again, since it's 1720, you might want to look at your NMR to kind of see if you have any aldehydes. And the aldehyde hydrogen would definitely be what we call way downfield. So the hydrogen in an aldehyde would be at between 9 and 10, and I don't have anything between 9 and 10. So that 1720, yes, is on the borderline, but because of my NMR, I could kind of tell that it's going to be a ketone. All right, so I have 7 carbons. I drew them out here, and I now need to look at my NMR. Well, my NMR is actually kind of nice. I have a triplet, a sextet, and a triplet. So triplet, sextet, and a triplet. And look at their numbers. There are 4, 4, and a 6. And what I've kind of told you before is if you have even numbers, chances are you have some kind of symmetry, okay? Meaning that functional group might be in the middle of that molecule. So anytime you see something that nice, start with that and see if it works. If not, then just move that functional group someplace else. Again, you can't have the double bond oxygen on the ends because then it would make it an aldehyde. And I don't have a hydrogen around 9 or 10. So let's see if I look at my hydrogens, if I would be able to reproduce this model. So again, triplet around 1 is always going to be, again, a CH3 group. So it's going to be these hydrogens that are on the end, okay? Because again, they only have one neighbor. Here's the neighbor, and it has 2 on it. I also want to look at, all right, the hydrogens that are right next to that C double bond oxygen, okay? Because those are going to be in a particular place on an NMR. So go to your sheet and find your carbonyl compounds. The hydrogen that is on the carbon that is right next door to that C double bond O is going to be between 2 and 2.7. So here is a triplet there. And a triplet would mean it only has 2 neighbors. So if I look at these hydrogens here, okay, they only see these neighbors right here, okay? That's all they see because there is no hydrogen on the carbonyl because you have that double bond. So if I take my highlighters and I highlight those hydrogens, it makes sense that it's going to be that triplet there. And that triplet has 4 hydrogens that see that environment. So those are 4 hydrogens that are a triplet. So the only other one I haven't discovered is these hydrogens here. And they are going to see a lot more neighbors because they're kind of in between. They're kind of in between. So the blue hydrogens see this neighbor that has 2 hydrogens, but then they also see the hydrogens that are on the end, okay? The hydrogens that are on the end. So again, this molecule has symmetry, so I'm just looking at one set because they kind of see the same environment. So I have 2 neighbors here, plus 3 more, so that's a total of 5, plus 1 is your sextet. So that's going to be your sextet here, the blue ones. So again, if you don't have colors, then just use arrows and point your way to each one of those peaks. And so that is going to be my molecule. And this is a ketone, okay? So ketones are going to have their naming system associated with it. And the name of this one, flipping around to find my answer because I can't remember off the top of my head. All right, so it is that C double bond O is in the middle of that molecule. So this one is called 4 because it's off the 4 one, heptanone. Okay, hept meaning 7, AN, kind of your heptane, drop the E and put the ONE on the end. So those are the first 2 problems on the integrated spectroscopy worksheet.